Hi everyone, Mr. Neighbor here, and today we're talking about 16.2, the nature of light. So, light waves and particles. At times, light acts as a wave, like we've been talking about recently, and at other times, it acts like a particle. That particle we call a photon. So, when we think of particles, think about like a physical object, like a little bead. That's a particle. So, it acts like a wave. Composition of a bunch of things, but also at times like a particle, a little bead of something. This was discovered by Max Planck and Albert Einstein. The behavior of light could not be explained completely by thinking of it as a wave, nor could it be explained by completely thinking of it as a particle. It only can be explained by thinking about it as both a wave and a particle at times. Super, super confusing. It goes down to the quantum realm, and it's very, very interesting. It deals a lot with probabilities where we never know exactly where that particle is going to land. It's only a probability where that particle is going to land. And that probability can be most notably determined when we think about it not as a particle, but as a wave. So, super, super awesome stuff when you get into the quantum realm. Very, very confusing, but if we can harness the power of quantum physics, we can bridge distances and not worry about connecting wires to bridge those distances. It will be a super tool for us to use if that ever happens. Who knows? But light waves and particles. Light particles. Light acts as tiny particles of energy called photons, which we mentioned above. It's used to explain how light works at atomic levels. So the photoelectric effect is when light bumps off electrons. Lasers, for example, that's when light forms parallel waves instead of spreading out like a wave. But when you do have light waves, when it does act as a wave, it is a transverse wave. So that's particles moving perpendicular to the wave. So the typical wave that you're used to thinking about, not the sound waves, which are longitudinal waves where they have these lines. It is a transverse wave. It is an electromagnetic wave, which means that it does not need a medium to travel through like sound does. It can travel in space. It doesn't need anything, or it can travel through a medium. When it does travel through a medium, it is distorted a little bit. It reflects and redirects itself slightly. So you can see that most notably if you stick anything in a glass of water, you will notice the object is slightly off from its physical counterpart that is not in the water. That's because when light moves through a medium, it is going to be redirected in some way. The speed of light is considered the universal speed limit. Nothing can go faster than the speed of light. The speed of light is 3 times 10 to the 8th meters per second in a vacuum, and it slows down in more dense material. So it's not as fast in when it goes through something. Light intensity. So intensity is how bright the light is. It depends on the amplitude or number of photons and the distance from the source it is. This is something that's measured in lumens, LM. Now let's talk about the electromagnetic spectrum. This is the range of wavelengths and how they appear to us, their sizes, and kind of where they come from, just to kind of get a grasp on everything. So we'll break this down into the different types of waves, but this is the whole spectrum as you see it right now, from the longest waves, radio waves, to the shortest waves, gamma rays. All right, first we have radio waves. They are the longest waves, and they're the lowest energy of light. So these include TV waves, radio waves when we use radar. These are invisible to us because they are beyond the visible light spectrum. So radio waves, size-wise, are the size of soccer fields, houses, or longer. They come from radio, and also, well, this is going to get into the microwave realm. but you can see the energy down here then. And then the frequency, waves per 1 second. Next, we have microwaves. They are used to heat food, but only can penetrate a few centimeters. So it's used in space probes to communicate back to Earth. Sources, a microwave, obviously, and radars will also use microwaves. The wavelength, you see it starting to get shorter. When you have 10 to the negative power, that means it's getting smaller. The frequency then is increasing because they are directly or indirectly related. As the wavelength decreases, then the frequency, the number of them, is going to increase, and the energy is picking up. It requires more energy for a microwave. Next, we have infrared light. So it's just outside the range of visible light. It's used in weather mapping and heat sensing technology and causes your car to get hot in the summer. So infrared light, its wavelength is the size of cells and bacteria. Sources come from people emit that, and at sometimes light bulbs. Actually, light bulb is in the category of visible, sorry. Next, we have ultraviolet light. This is just outside the range of visible light. It causes sunburns and leading risk of skin cancer. A lot of it's deflected by the ozone layer, but if the ozone layer is decreased, then we have more UV rays that are penetrating and harming our skin. So that's why we are so concerned about sunscreen and the ozone, because we do not want ultraviolet light to hit us, because that's the health hazard right there. So things that don't have ozone layers, it's really hard to have life on there. So that's why when we think about going to Mars or the moon or somewhere like that, there is no atmosphere, no ozone layer. So the UV rays are penetrating, and that's the health hazard. So in those instances, we either have to think of creating an atmosphere or thinking about living underground, because the UV rays would shorten our lives, because it would be bad for our health. Next, we have X-rays. They are used in medicine to image bones, but lead shields are used to avoid exposure to the radiation. So these are getting into the size of proteins and water molecules. So X-rays are getting down there to the tiniest ray, or wave, sorry. And lastly, we have gamma rays. They are the shortest wave, and they are the highest energy of wave of light. Radiation therapy that shrinks tumors and kills cancer cells is used. It uses gamma rays, but it also puts patients at higher risks of recurrent cancers. So it might get rid of some, but it also may cause some. So notice it is the shortest wavelength, it is the largest frequency, and it has the most energy associated with it. The last thing I would like to talk about in this video is additive and subtractive colors. So a lot of times we think there are 6 colors, but really the primary colors that we're concerned with depend on if we're talking about subtractive colors or additive colors. So if we're talking about subtractive colors, I think this is what most people think of, where you're taught that as light comes down, if every part of the light is absorbed, that means you have black. Black is absorbing everything. If you have white, everything is being reflected. This is an example of subtractive colors. Additive colors, however, are when you're thinking about a computer screen. It's completely black. You need to add colors. And when you add all the colors together, you get out white. So notice that there is some similarities. Here we have magenta as the secondary color. Here we have magenta as the primary. Red as the primary. Now red's the secondary. Yellow was the secondary. Now yellow's the primary. Green was primary. Now green is secondary. You're starting to see the pattern that whatever's primary over here is secondary over here. Whatever's secondary here is primary over here. So it's just a different way of looking at light, depending if you're talking about screens or printers, or how light is coming from the sun. So additive colors and subtractive colors.